Welcome learners to the channel Black Slides Online Secondary School. Remember this, on this channel you have the privilege to learn the sciences for free. Alright, so you'll be able to access the real-time lessons in physics, chemistry, mathematics and biology, but in the near future, closer than we've been talking, you should be able to have a full Msce curriculum delivered here and also delivered in our online secondary school, so that by just registering with Black Slides Online, you should be able to stay back at home and learn at your comfort and at your pace, okay, minding the imminence of having an exam in a stipulated period. Like right now, we are expecting some of you to take your Msce exams in July. So always keep visiting the channel, and by virtue of being subscribers to the channel, you will be getting regular notifications whenever a new video lesson has been uploaded. Right, so in case you are new, let me welcome you to the channel, and feel free to interact with the material as well as us teachers by asking us questions where you don't seem to follow on. All right, you can send us a message, direct message on the number shown, and we'll be able and glad to come back to you with a timely response. Without much ado, let me welcome you to today's lesson in the Msce Physics. We are meeting now for a topic called radioactivity. It falls under a core element called nuclear physics. This is a part of a main topic called nuclear physics, and in particular we are going to be discussing radioactivity of elements. All right, so once again, my name is Mr. Poch Lola, and if you have just access to this channel today and you have not yet subscribed, let me advise you to like, subscribe, and hit the notification bell, so that every time a new material is uploaded, you are the first one to see it and learn. So do yourself that favor by hitting the subscribe button as well as the notification bell. We wish you happy learning. Very quickly, let's look at why we need to learn radioactivity. What is it that we are targeting to know by looking at the specific objectives? So by the end of this topic, radioactivity, you, the learner, should be able to do the following. You should be able to give definition, to define radioactive decay, and to define what is called half-life. All right, so you should be able to define radioactive decay and half-life. Your examiners will simply ask you define radioactive decay or define half-life. So this lesson is going to help you understand the definition, to know the definition of radioactive decay as well as half-life. Right. You should also be able to describe the 3 types of radiations which are emitted in natural radioactivity. Right. Okay. Describe the 3 types of radiations emitted in natural radioactivity. 3 types of radiations. Right. Should also be able to explain the different methods of detecting, all right, explain the detection of radioactive emissions. So describe the 3 types of radiations and then explain the detection methods of radioactive emissions. All right. You should be able to define nuclear fission and nuclear fusion. Please take note. Nuclear fission and fusion. Okay, should be able to write balanced nuclear equations. Should be able to write balanced nuclear equations. Should also be able to explain the dangers of radioactive emissions. So these are the things that you need to be able to do once you have learned this topic thoroughly. So these are the indicators that indeed you have learned. If you are able to perform these tasks, then it means that you have truly understood the topic and you are ready for the exams. All right, in the topic, we are also going to state the applications of radioactivity. State the applications of radioactivity. All right. And then you should be able to solve numerical problems involving half-life. Numerical problems involving half-life. Okay. So these are the key objectives of this topic. So give definition of radioactive decay and half-life. Describe the 3 types of radiations emitted in natural radioactivity. Explain the detection of radioactive emissions. Define nuclear fission and fusion. Write balanced nuclear equations and explain the dangers of radioactive emissions. Then state the applications of radioactivity. Solve numerical problems involving half-life. These are the areas which your examiners expect you to be able to perform. All right, so once again, my name is Mr. Poch Lola. Now, the key terms that you are going to meet in the lesson, in this topic, we are going to meet terms like radioactive decay. Okay, so what is it? Okay, what is radioactive decay? You are going to meet terms like half-life. Okay, we are going to meet terms such as radiations, properties of radiations. You're going to meet terms like detectors of radiation. You meet terms like nuclear fission, nuclear fusion. And then we are going to look at nuclear equations. And later on, towards the end of the topic, we'll look at hazards or dangers of radioactivity and their precautions, the things you need to do in order to prevent the hazards associated with radioactivity. Then we'll talk about applications. So these are the key terms and the processes which you are meeting in this topic as we discuss the topic called radioactivity. We'll also look at problems of half-life without considering the integration of it, like calculus. Yeah. So we'll not tackle the calculus part of it. We'll just dwell on the basic problems. All right, so some introduction is going to be of help as we begin to look at the topic. First of all, let us define the term radioactivity. I always say that the way to unlock the understanding of a topic is to first of all understand its definition. All right, so radioactivity is basically the disintegration of an unstable nucleus with emission of radiation in order to attain stability. That's how we are going to define radioactivity for the time being. So in the definition, we have terms like disintegration. To disintegrate simply means to break down, to break, particles breaking. Okay? So what is being broken is the nucleus. That nucleus is an unstable nucleus. So it's the breaking down of an unstable nucleus, okay, which is followed by release or emission of radiation in order to attain or to obtain stability. So already the definition is telling you why an unstable nucleus break down. They break down in order to become stable, and also the process is accompanied by the release of radiation, which we are going to discuss as we go along. So define radioactivity as a question. It is the disintegration. To disintegrate means to split or to break down. It's the breaking down or the splitting of the nucleus of atoms which are not stable, and the process is followed by emission of radiation. Why there is need to emit radiation is in order to obtain or to become stable. So why should certain nuclei of atoms disintegrate? It's in order for them to become stable, and the process is associated with the release of radiation. Right, so that is the definition of radioactivity there. Now, for us to understand this further, let us revisit the structure of an atom, which you might have covered already in chemistry, but it would be worth looking at again. All right, so what is the structure of an atom, or what is an atom made up of? When we are looking at the structure of an atom, we are basically looking at the makeup of the atom. What is the atom made up of? All right, so an atom basically consists of tiny nucleus and the energy levels. All right, that's what makes up an atom. So in the very center of an atom, there is a very small nucleus, and surrounding the nucleus are the energy levels, which are also called shells or orbitals in some cases. All right, so the nucleus is very small in size as compared to the overall size of an atom. All right, so the size of the nucleus is very, very small compared to the whole atom. All right, so in the nucleus, you find particles which are called subatomic particles, namely protons and neutrons. So protons and neutrons are found in the nucleus. All right, so the number of electrons in the shells is equal to the number of protons in the nucleus, making the atom electrically neutral. Take note, we are saying that in an atom, the number of electrons. Remember that electrons are negatively charged particles found in the shells. So the number of electrons is equal to the number of protons. Okay? Remember, protons are positive, electrons are negative. So if the two are equal in number, the atom becomes electrically neutral. Okay? All right, so basically that's the composition of an atom. Let's look at, for example, an atom of a hydrogen atom. All right, so we are saying a hydrogen atom has a nucleus. The one that is shaded, it represents a nucleus. Inside it, there is one proton. So since the number of protons equals to number of electrons, there is one proton in the center, then the nucleus, and one electron in the shell. So this makes the hydrogen atom electrically neutral. Why? Because a positive particle added to a negative particle, like positive 1 added to negative 1, it will give you 0, a net charge of 0. All right, so a hydrogen atom is electrically neutral because it has one proton and one electron. Another atom, example of an atom, is that of helium. A helium atom has 2 protons and 2 neutrons, but at the same time it also has 2 electrons. There's this electron here and this electron here. So the number of electrons in the shells must equal the number of protons in the nucleus. So that makes a helium atom electrically neutral. Because you have positive 2 and negative 2, it is going to give you 0 charge. Okay? Another example of an atom is that of neon. Remember, neon is a noble gas just like helium. Its nucleus contains 10 protons and 10 neutrons. The number of protons equals to number of electrons in the shells. So you have 2 here, you have 1, 2 in the first shell closer to the nucleus, and 8 electrons out to outside. So when you add 2 electrons to 8 electrons, that makes it 10 electrons, which is equal to 10 protons. So positive 10 plus negative 10, it gives you a net charge of 0. So that's basically the structure of an atom, just reminding you from your chemistry lessons. All right, so remember to like, subscribe, and hit the notification bell so that you don't miss any lessons that are uploaded from time to time. All right, further introduction. There are some important terms which are key to understanding this topic, such as atomic number. Atomic number, as you learned in chemistry, refers to the number of protons in the nucleus of an atom. Okay, sometimes we call this proton number. How many protons there are in the nucleus of an atom is the atomic number of that atom. All right. So the atomic number of hydrogen, for example, is 1, and that of helium is 2, and that of neon is 10. All right. So the number of protons that are there in the nucleus of an atom is called the atomic number. Another term which is also very key to this topic is the mass number, also known as nucleon number. Okay, if you thought mass number refers to the sum of protons and neutrons, then you are right. So we are saying when you take the protons and neutrons in the nucleus, add them up, then you have what is called the mass number. What is mass number again? It's the number of protons and neutrons together in the nucleus. For example, if you look at neon has 2 protons and 2 neutrons. The sum of 2 protons and 2 neutrons is 4. That means the mass number of helium is 4. All right. Then we have another concept related to the topic, which is called isotopes. Isotopes, all right? Isotopes refers to atoms of the same element that have the same atomic number but different mass numbers. Okay, there are some elements we having the same number of protons but different mass numbers. Okay, think about carbon. We have three isotopes of carbon. Namely, we have carbon 12, carbon 13, carbon 14. All these carbon elements have the same atomic number of 6, but different mass numbers. In one type of carbon, we have mass number of 12. In another, we have mass number of 13. In the other one, we have the mass number of 14. Yet, all of them contain the same number of protons, which is 6. All right. Similarly, we have two forms of chlorine. We have chlorine 35 and chlorine 37. Those are mass numbers, but both of them have the same atomic number of 17. So those are isotopes. Hydrogen also has three isotopes. We have hydrogen 1, which is called protium, hydrogen 2, which is called deuterium, and hydrogen 3, which is called tritium. So we have hydrogen 1, hydrogen 2, hydrogen 3. Those numbers I'm mentioning are mass numbers, yet each hydrogen has an atomic number of 1. All right, so isotopes are basically the same elements that have the same atomic number, but when you look at their mass numbers, they are different. The difference in the mass numbers is basically due to the difference in the number of neutrons in the nucleus. Okay, right, so that's the isotopes. Another term that is also very critical to this topic is a nuclide. A nuclide, by definition, is simply a group of atoms that have the same atomic numbers and the same mass numbers. A group of atoms that have the same atomic numbers and the same mass numbers are referred to as a nuclide. Right, in case you have questions, don't forget to leave a comment in the comment section, or you can directly send us a message on the number that is given earlier on, and then we'll be able to attend to you. It is you that we value. It is you that we would like to have on this forum, and we will see you progress and succeed. Please learn as much as your brain can allow you. Another important term that we need to consider is nuclear stability. What makes some atoms stable and the others unstable? All right? Okay. So nuclear stability has to do with the stability of atoms, especially the nuclei or nucleus of atoms. Stable nuclides or elements have proton to neutron ratio of about 1:1, meaning that in such atoms the number of protons is equal to the number of neutrons. Atoms whose number of protons and neutrons are equal are in most cases stable, which means that their nucleus has very low probability of disintegrating. All right? But there are times when atoms get heavier and there is a marked deviation from this ratio, with the number of neutrons far superseding that of protons. In other words, number of neutrons becoming greater than number of protons. I'll give you an example. If you look at carbon 13 has 6 protons and 7 neutrons, which means it has a greater number of neutrons. That will make it unstable. So in such circumstances, the nucleus is likely to be unstable. So what causes instability of nucleus or nuclei of certain elements is an inequality of protons and neutrons. When you have more protons than neutrons in an atom, in the nucleus of an atom, such an atom is most likely to be unstable. So what is going to happen is that the atom is going to disintegrate so that it achieves stability, so that some particles are released in order to ensure that the number of protons and neutrons is the same. All right? So we are saying that atoms whose number of protons equals to number of neutrons are most likely to be stable. But there are times when the number of neutrons is greater than the number of protons in the same nucleus. Such atoms are going to be unstable, and they are going to break down in order to release some particles so that they achieve stability. Very important this point is in relation to what we are discussing today. All right, so this graph shows how the number of protons and number of neutrons changes. Okay, so there are times when the graph is showing us two possible regions. This one which is marked X, and this one marked Y. Okay, so these two regions represent regions occupied by unstable nuclides. Okay, and the line passing through the middle between these two regions represents a line of stable nuclides. Okay, so we are saying that when the number of protons and neutrons is the same, then stability is achieved, represented by the line which is symmetrical passing through the two regions, this red part. But as the number of neutrons gets greater than number of protons, then the nuclei become unstable with the high probability of having their nuclei disintegrate, so that some particles are emptied from the nucleus in order to achieve stability. I hope we are moving along very well together, very well. And just in case you are behind or you are not following, please raise an alarm. Tell us that we need to explain some concepts back to you. It is our job to help you understand so that come exams, you pass very well. All right, so welcome to a process called radioactive decay. Please pay attention to the definition of radioactive decay and relate this definition to a process which we call radioactivity. All right, so what is radioactive decay? Radioactive decay, by definition, is the process by which a radioactive nuclide, all right, undergoes disintegration to emit radiation. Okay, so think about a radioactive element such as uranium, for example. Okay, so when its nucleus, when the atom splits, breaks down, disintegrates to release radiation, such a process is called a radioactive decay. Since it involves a radioactive element, so the process is called radioactive decay. An atom undergoing a disintegration with the release of radiation is called radioactive decay. So the emitted radiations can be alpha particles, beta particles, and This is accompanied by release of energy in form of gamma radiations. Okay, so we are saying the emitted radiations can be of three types: alpha particles, beta particles, and the gamma radiations. Notice that it's only alpha particles, it's only alpha and beta that are particles. Gamma is not a particle, it's a pure radiation, right? But it is associated, gamma radiation is emitted in the course of emission of alpha particles and beta particles. Okay, so whenever alpha particles and beta particles are emitted, the process will be accompanied by the release of gamma radiations. Please take note of that. So there is alpha particles and beta particles, and then the process is accompanied by the release of energy, which is in form of radiations. Remember that the gamma belongs also to the electromagnetic spectrum among the different types of radiations known as electromagnetic radiations. All right, so notice that gamma radiations is not a particle, it's purely energy, electromagnetic energy. All right, so take note, whenever an atom disintegrates, it emits alpha particles, it emits beta particles, and this is accompanied by release of energy in form of gamma. So basically there are three types of radioactive decay. The first one is alpha decay. So alpha decay is a radioactive decay in which alpha is released by the nucleus of an atom, and an alpha is represented by a helium nuclide. Okay, in other words, alpha particle is similar to a helium nuclide. Remember that a helium nuclide has a mass of 4 and the atomic number of 2. This means that it has two positive charges, which are basically protons, and it has a mass number of 4. Remember, mass number is the sum of protons and the neutrons. So we have 2 protons. That means there are also 2 neutrons. When you add them up, they give you a 4 there. So the symbol for an alpha is an alpha letter. It's a Greek letter which is written like that. So if you're using a pen, you'll write your alpha like that. That's an alpha particle. An alpha particle. So an alpha particle is similar to a helium. It has a mass of 4, a mass number of 4, and the atomic number of 2. All right. So take note that this is the symbol. When you are writing equations, don't forget this is the symbol you include in the equation, bearing on your mind that it has a mass of 4 and the atomic number of 2. Mass of 4 and atomic number of 2, just like helium. Helium is has a mass of 4 and atomic number of 2. Remember, the 2 represents positive charges, which are protons, and the 4 represents the sum of neutrons and the protons added up. That's called mass number. Mass number. All right. If you are okay with that, I'm glad. So an alpha particle or alpha decay is released. The mass number decreases by 4 and the atomic number decreases by 2, as shown here in this equation. Let's suppose that an atom represented by the letter X is undergoing an alpha decay, or is emitting or releasing an alpha. So the X here represents, this X represents an element. The A on top represents its mass number, and the Z or the Z below here represents atomic number. So let's suppose that this is emitting an alpha particle. So its mass is going to decrease by 4 and its atomic number will decrease by 2. The element which is formed is different from the original element. Okay, so the product is different from the area element, the original element. So what this means, in case you cannot see this clearly, we are saying that if X is an element, so that its mass is A and its atomic number is Z, from this you take away an alpha. You take away an alpha, which has got a mass of 4 and atomic number of 2. What is going to be formed is a different element altogether, which so that its mass is going to be the original mass minus 4 and the original atomic number minus 2. So when you cross this, you take this to this side, then it will be like you are adding, you are basically adding. So the equation now is going to be, X, the element with mass number of A and atomic number of Z. The equation is going to be like this. You have a new element Y with a mass number 4 less than the original and atomic number of 2 less than the original, and then to this you add an alpha which has got a mass of 4 and atomic number of 2. Notice that this is similar to a helium nuclide. It's similar to a helium nuclide. Alright, so in this case the original element is called parent nuclide and the new element is called daughter nuclide, and then you have an alpha particle. Remember, an alpha particle can be represented like this, or the Greek letter alpha with mass numbers shown on it. By the way, I think this was a typing error. Over here the 4 is supposed to be on top, so we have HE 4 on top and the 2 down there. Right, remember to correct this. It is a typo mistake. All right, so let's see how far we have gone so far, and I hope so far so good. In case you have questions, don't hesitate to give us a call or to comment in the section, in the comment section, for us to explain again. It is going to be our pride to repeat explaining this to you. All right, so for example, let's look at uranium. Uranium decays by emitting an alpha to become a different element, which is called thorium. So the decay process is represented as shown in the equation here. Look at the original quantities. Uranium has a mass of 238 and the atomic number of 92. So when it decaying by alpha decay, it is going to have its mass reduced by 4. From 238 subtract 4, you have 234. Alright, check that the numbers are adding up, they're balancing up. If you add this number to this one, it must give you 238 there. Similarly, the number of protons or positive charges also has decreased by 2. To just subtract a 2 down there, it will give you 90. So that when you add 90 to 2, you should be able to get 92. Alright, so this is an example of an alpha decay. For you to be sure, check that the numbers that are on top, when you add them up, should give you the original mass. Similarly, the numbers at the bottom, which are positive charges, protons, should add up to the original number, the atomic number, which is 92. All right. And in a similar way, polonium undergoes alpha decay to become lead metal, as shown here. So we have polonium with a mass number of 210. When it loses a mass of 4, by taking away 4 from 210, you get 206. The atomic number is also going to decrease by 2. 84 subtracted 2 is 82. And similarly, when you add these numbers up, 206 add 4, you must get 210. And 82 add 2 must give you 84. So in this case, polonium is the parent nuclide, and the lead metal becomes a daughter nuclide, and then we have an alpha there. Very, very important to note. Let's look at what happens when an element is undergoing a beta decay. A beta decay means the element is releasing a beta particle. All right, so a beta particle is basically an electron, which is represented by E and a mass of 0 and a charge of -1. So this is 0 here indicates that a beta particle has no mass. But it has a charge of -1, and is denoted by this symbol here. It's the second letter in the Greek alphabet, which is called beta. All right. So if an element or a nuclide undergoes a beta decay, the mass number remains the same, because we are just subtracting 0 from whatever number we have on the parent nuclide. So the mass number remains the same, but the atomic number increases by 1. Okay, as this example shows, we are going to see why the mass number increases by 1. All right, so let's suppose that we have an element X whose mass number is A and the atomic number is Z. We are saying that the mass number is going to remain the same because you are subtracting a 0. When you subtract a 0 from a number, the number remains the same. A number minus 0 is equal to the same number. All right, but the atomic number increases by 1. Okay, why does it increase by 1? It's because you have the original one is Z, and then you subtract from this an electron which is negative. All right, the result is going to be a Z. A negative followed by a negative is a plus, so it will be +1. We are going to see an example shortly. Okay, so also check that when you add this Z +1 to -1, you should be able to get back to Z, because this +1 plus -1 should give you 0, which brings us back to Z there. All right, very important to note. This change. All right, so once again, we have the X here, which is the parent nuclide, and the daughter nuclide is a different element, which is Y. And then we have a beta particle there. Please take note of the format of the equations known as nuclear equations. So think about sodium, which is a radioactive form of sodium. For example, will undergo beta decay to become magnesium. Sodium metal becoming a magnesium. So we can write the equation like this. Sodium, which has got 24 mass number. Of course, the normal sodium has a mass of 23, but this radioactive isotope has a mass of 24 and the atomic number of 11. All right. So when a beta is being released, the mass is going to remain the same, but the atomic number is going to increase by 1 from 11 to 12. How this happens? You have 11 subtract a -1, which is the charge on the electron. This is going to give you 11, add 1, which is equal to 12. All right, which is equal to 12. So take note of these changes. Once again, in case you have questions, don't hesitate to contact us or to leave a comment in the comment section below, or simply give us a text message on the number that has been given to you. an example. Thorium 230, which is given by this nuclide symbol. We have 230, mass of 230 and atomic number of 90, undergoing a decay to become radon with mass number of 222 and atomic number of 86. Find the number of alpha particles emitted. All right, so we want to find this x here. What is the value of this x? So as we saw earlier on, let the number of alpha particles emitted to be x, this one over here. So the expression for the decay is going to be thorium releasing a certain number of alpha particles. How many? X, we don't know this. Okay, so what is going to be the value of x? Okay, so first you write your equation as follows. You remove brackets by multiplying x by 4 and x by 2. So when you remove the brackets, you're going to have 230 being equal to 222 plus 4x. So solving for x, it will give us 2 here. So you take 222, subtract from 230 to give you 8. Then you divide both sides by 4, you get x is equal to 2. In the same way, if you take the atomic numbers, you have 86, add the 2x, and then solve for x, you still find the value of x equal to 2. That means that 2 alpha particles were released in the process. Another example will help just to consolidate what we have learned. Lead metal of mass number 214, written like this, decays to polonium 214, written like this, by emitting beta particles. Calculate the number of beta particles emitted. Once again, let x be the number of beta particles emitted. So our equation is going to look like this, and then you multiply through by x. So x multiplied by 0 is going to be 0, because an electron or beta has no mass, so this is going to be 0. Therefore, we cannot use 0 up there to find x. So rather, we can use the -1 and the number of nuclides, which we don't know. All right, number of beta particles, which you don't know yet. Okay, so when you remove brackets, you multiply x by -1, you get and you add this to 84. So it will give you 84 minus x. 84 minus x, and you equate this to 82, and then you solve for x, it will give you x equals to 2. Therefore, there are 2 beta particles that are emitted in the process. Right. Our last example is looking at uranium 238, written like this, undergoing decay to become lead with a mass number of 206 and atomic number of 82. Find the number of alpha and beta particles emitted in the process. All right. So here we have uranium undergoing a decay in which both alpha and beta are emitted at the same time. All right, so let number of alpha and beta particles be x and y. X and y. Okay, so we can put I think here we need the y. Over here we need a y. Okay. All right, so we can now write our decay equation like this. So we have uranium, which is becoming lead, but then a certain number of alpha particles and the beta particles was emitted. Alright, so expanding accordingly, removing brackets and rewriting the equation shall give us these two equations from which we can solve for x and y. Simultaneously, you find x is equal to 8 and y is equal to 6. Alright, so for now, let me leave you. And like I always encourage, make sure you get similar questions and practice. And you may wish to show me so that we can share knowledge together and ways of solving these problems together. My name once again has been and is Mr. Poch Lola. Thank you very much.